Hello, everybody. Today is our fourth lesson in a series of application of IQmol plus our Q-Chem system. And to illustrate their how this system operates, I will use another example from chemical reactions, which are quite popular in this type of reaction called electrocyclic reactions. And I will use their simple example, simple in the sense of a number of electrons or atoms involved, transformation of butadiene into cyclobutene or vice versa. And these reactions are terminal carbon in butadiene form the bond which make a four-member cycle, and the pi bond transform in the way that one of the pi bonds between the two pi bonds of the terminal carbons, they form a sigma bond, and in the two terminal pi bond, they become sigma bond, and their central bond, it become two double bond with pi bond. So in order to make such reactions, we will need in case of closing the cycle, we will need to rotate CH2 group of terminal carbons. This rotation can be done in two ways, in principle. We can rotate it on one side, which called conrotatory, or we can rotate it one to each other on one side of the plane. This would be called disrotatory. So I will just made a handmade drawing for this for these two possible processes. Okay, so both a reactant, in this case we consider butadiene, and the product cyclobutene. So they both have C2V symmetry, which means they have two planes. One is a molecular plane, another one is perpendicular to molecular plane, in the twofold axis. So we can rotate their left or right side of the molecule 100 degree, and we'll get the same molecule. So there's two way to rotate it, as I mentioned, in order to form the cycle. One which would preserve twofold axis, so its rotation on one side, it's called conrotatory, and another side where we will preserve the plane perpendicular to the molecular plane. So these two hydrogen go to one each other, and those go further away from each other. So this is, as I say, is conrotatory process, and this is disrotatory. So there are so-called Woodward-Hoffman rule for this type of reaction, and this is the most simple example, where they explain which reactions might occur thermally and which will occur photochemically. And in this case, the rule is if symmetrically the occupied orbital pi system transform to mixed pi and sigma bond system, preserving the symmetry of the occupied bonds, then it's thermally allowed. If we would need to symmetrically connect, by symmetry connect occupied and non-occupied orbital, so this process will be forbidden thermally, but may occur photochemically. And this explains the stereochemistry of this type of reaction. For the simple example and for much more broad class of what is called electrocyclic or pericyclic reaction. So this is an example of conrotatory, where we preserve their C2 axis or twofold axis. So this is their pi orbital of butadiene, and this is the orbital of cyclobutene, which relate to them. So and when we rotate this molecule around twofold axis, so the lowest occupied orbital, pi orbital, so it's totally symmetric. It's anti-symmetric to this rotation. You can see if we just flip this side, so the change, the sign of their pi orbital will change. This one, which in this case is anti-bonding in the center, so this would become symmetric to whole rotation, and so forth. So for cyclic system, so the rotation around 100 degree of sigma bond will make it symmetric, but for pi bond it's anti-symmetric, and so forth for a non-bonding orbital. And as we might see, we might just correlate to each other their lowest pi orbital to the pi orbital of the cyclic system, and this highest occupied orbital is related to the sigma orbital. So in this case, this process is thermally allowed because occupied orbitals are related symmetrically to to occupied. In case of disrotatory rotations, so for a cyclic system, reflection in the plane make both pi and sigma orbital, bonding orbital, symmetric, and non-bonding orbital, the anti-symmetric. While in case of Butadiene, so the lowest occupied, the most symmetrical orbital is symmetric to reflection in the plane. The second one, which is highest occupied orbital, is anti-symmetric. And next one, first non-occupied, is symmetric. So toward the our reflection in the plane, and the next one is anti-symmetric. So in this case, we connect the lowest orbitals from Butadiene system to the pi bond in cycle, but in case of two next orbital, they intercross. In this, they interconnect in their Butadiene system highest orbital is related to non-occupied orbital of their cyclobutene system, and their pi bond of this Butadiene cyclobutene is related to non-bonding orbital of lowest non-occupied orbital of Butadiene. So, and this process is allowed photochemically, but forbidden for thermal reaction. Okay, so now I will do calculations with IQmol and Q-Chem system. So let me just share the screen and open the IQmol. So what I'll do first, I'll just show you how do I build the systems, which is relatively simple process. So just building is of cyclobutene is creating their 4-member twin. So let's not make one of the double bond, add hydrogen, then make it optimize it with molecular mechanics. So, and then it can be computed. Actually, I pre-computed them already at MP2 level, and I'll show you the result at the end for geometries of all the system I calculated. Now, let me show you how I build the Butadiene. So let's just remove it. So I'll just repeat the same action. So only in this case, I would not form the cycle, but make this double bond, terminal double bond. So then I will add hydrogens. So, and then I'll optimize it. Okay, so that's how I did build the Butadiene and did the calculation. So I'll show you the calculation only for one case, namely the most difficult one, a transition state. In order to get the first gas structure for the transition state, I use the same trick I already used in my previous example, the lessons before this one. So what I do, I temporarily replace this hydrogens by an oxygen. Optimize this with molecular mechanics, then remove oxygen, and then add the hydrogen back. Okay, so now what I do, I create the gas structure for transition state disrotatory by rotating by arbitrary 45 degrees. So in this case, what I need, I don't need this one. Okay, so I make highlights for atoms in order to calculate this angle. So in this case, I go to build, click on set geometry constraint. It shows the 0 degree. So what I need to put, arbitrary 45 degrees that by my experience and apply. Okay, so this rotate one CH2 group in one of the directions. So what I do, I just repeat the same for the other side. So again, I highlight. Okay, so I don't need to highlight bonds, but sometimes it's tricky. So let me just remove some of the highlights I don't need. Okay, so all right. So okay, now build set geometry constraint again 0, and I will put 45 degree again. Apply. And as you may see, so I get there I get their conrotatory structure. So, and now I set the go to calculation. Q-Chem setup. Job 1 will be a transition state. And job 2 will be at job 2, which will be our frequencies. Okay, so I'm going to go and submit. I'll just call it TS, transition state. Okay, let's go. Okay, so now, well, it calculated. So meanwhile, our calculation is going. Let's see job monitor. Let's see where is my job. So it's now running. Okay, so now I go to what I will do at this time while calculation is going. I open the previous result for Butadiene. So okay, oh, actually it's finished. All right, so finished result transferred to the server. Okay, let's just put it in test. Select folder. Okay, directory exists override. Yes. Okay, so the star showed that the calculation was successful. So in order for us, and let's see the structure. Yeah, it's indeed show that it's kind of similar to the draft I made. And in order to confirm that it's right transition state, so I go to frequencies, and so there is one imaginary frequency, and if I double click on it, we'll see that this vibration is correspond of forming and breaking the bond in a cycle. So just for curiosity, let's look how their lowest occupied in highest occupied and lowest unoccupied orbital look. So let's go and calculate them. Okay, so it showed that I calculated the highest occupied orbital and lowest non-occupied. So that's how it's look like, because it's slightly rotated. So it show it it's an interesting, like two sausages around each other. So with bonding on one side of the molecule. So okay, so let's see how the lowest non-occupied look like. So look kind of similar, but they are opposite to each other for direction. So in this case, what we did, we computed their transition state for this reaction. So let me just show you my calculation for let's just file add new molecule. And I just simply add the results of what I already calculated here for butadiene. So I go and open directory. When you already have calculation, you open the directory. So that's my calculation for butadiene. Select folder. So this is my calculation for butadiene. And what I want to show you is this is the four orbitals, two highest occupied and two lowest non-occupied orbitals. So I go here. So it suggests me as a default to calculate the highest and occupied and lowest non-occupied. So I add one more here. So one below the highest occupied and one above lowest unoccupied. So I do the calculate and see what we get. So this is so we'll see I had calculated 4 orbital. 2 of them are occupied and 2 non-occupied. So it shows me their highest actually one or below the highest occupied orbital. And indeed, it's as you may see, it's a bonding orbital of pi bond system, which is our overlap of 4 pi orbital. So let's now look at the highest occupied orbital. It's pi orbital, which is in the area of bonding in the area of connecting to these two bonds terminal carbon atoms to their central atoms. So there's bonding in this area and anti-bonding in the central part. So this is this is exactly what is in the scheme suggested by Woodward-Goffman rules. Let's take a look at lowest unoccupied orbital. Yeah, it's indeed from the same type. So it's show the bonding in between the central atoms. As you can see, there is bonding among them, and anti-bonding in the area of the what is formally shown as pi bond. Okay, so let's just for curiosity look at the next one. However, so this is no longer pi orbital. It's actually this orbital is located more on a hydrogen. So let's go back to the this this picture I showed you before, and so this is a result of a calculation of MP2 631G level star level, and as you may see, I put here the calculated bond lengths for all structures, all 3 structures. So butadiene, cyclobutene, and the transition state. So as you may see, so this in case to butadiene, so the double bond is shorter. So this is single bond is longer. However, if you may compare with single bond in cyclobutene structure, so it's somewhat shorter. So this is non-bonding distance between these terminal carbons, and this is a bond in the cyclobutene. And as you may see in the transition state, it's kind of right in the middle between them. So for the transition states, you may also see, so this bond is getting shorter, so because it's going to direction of double bond, and this bond is elongated. So the transition state is really kind of geometrically is kind of in between the initial butadiene and cyclobutene. I also calculated the energy. So the energy at this level of theory there, the cyclobutene is laying about 4 kilocalories higher than butadiene, and the transition state is about 40 kilocalories above their butadiene. So that's what I get for this calculation, and let's resume our lesson. Thank you very much for your interest. Bye-bye.